So, last time we talked a lot about some filtrations. It was a necessary thing to do. Though usually in courses like this, we do not talk much about filtrations, as they usually start with building integrals directly from scratch. Uh, I think it's kind of important because you are supposed to be PhD students, most of you at least, and it's important for you to understand why every time you meet something related to stochastic integration, you might find this reference to standard assumptions. So we did this work to understand how the filtration of Brownian motion works, the counterintuitive thing about making it right continuous, which is not, which is contradicts the idea that this is a information stored in filtration a bit, because we need a glimpse of future. And we have now understanding why you need to do something with the filtration. So not just so we can at least understand what is happening, not just be, be a user of this terminology. So let's start with recalling what we already did. So we have omega fp is a complete probability space. Basically, W is Brownian motion in it. Ft is it's augmented in both senses, so it's right continuous, and it's augmented with sets of null measure, null set so-called filtration. And it says that we cannot easily define integral from 0 to t f of s dws because variation, so-called p variations of Brownian motions, which is supreme over all partitions, finite partitions of some interval where this integral is considered, of such sums k from 0 to n minus 1 of such difference to the power p is almost surely infinite for all p's that is less than 2. However, v2 of w, as we proved last time, exists in mean square. It also exists almost surely, but we only proved this part. And this like an indication of what of the fact that we need to proceed in L2. Now we consider the so-called progressive processes. So what is progressive or progressively measurable? A process psi of t, where t belongs from 0 to t, is called progressive. Progressive if this s omega, the mapping that takes s from a smaller interval and all omega, if the mapping is measurable as a mapping, a function between 0 t times omega with the product sigma algebra, borrow 0 t times ft and just RD with standard Borel-Silver algebra in RD for any t. So the restriction of this process is measurable in this good sense. Let me consider an example. That if tau is almost surely finite stopping time, and I will repeat this, stopping times are defined with respect to some filtration, but we have fixed filtration right now. So I will just say stopping time, and psi is progressive. Then the process, which can be described as stopped psi at random time t, is again progressive. And we effectively proved this, so I will not repeat the proof. I will just make a remark that I think I missed one set, the final expression. And if you look at that proof, what is also interesting, you will understand how it is constructed, because you start from the very beginning. Maybe we can like just repeat it quickly. Fix t less than tau, and because the proof is very standard, so let's repeat it, because this is the most important stuff in this course, like ideas of proofs. So if this new I is measurable, from this is exactly the sigma algebra that it's used in the definition of progressively measurable processes into the same sigma algebra, then the composition psi of tau minimum t minimum tau, which is exactly psi composition of E of t, is again measurable because as a composition of measurable functions. So this means it's progressive. And since we have something that involves minimum, we want to decompose everything related to this minimum into two cases where tau minimum t is equal to t and is when it's equal to tau. In the very same way, when you were calculating some distributions of minimum to random variables or random variables and a number. However, if you try to do this, you will understand that it's you need to consider, instead of the original filtration and any set from here, a good set that generates the collection of which generates a sigma algebra. And in this case, it is sufficient to consider such sets. And why we need sets of such form is going to be clear in a minute. So we just consider tau I to the power -1, which is inverse of sets of such type. Because to check measurability with respect to some sigma algebra, we need to check measurability with respect to the collection of sets that generate this sigma algebra. Now this is R from 0 to t. So we have fixed numbers S, we have fixed number t, and we have t capital, the original interval in which our set was defined, omega belonging to this, such that tau omega minimum R is less than S. And omega also belongs to F. Now we have obviously r less than t, omega belongs to f immediately. We need to consider like two cases here, exactly as I said, if you were calculating some probability related to taking minimums of two random variables. So there are two possibilities when tau omega is less than s and tau omega is greater than s. So if this is easier, I think. Let's see if I'm right. If tau omega is greater than s, we effectively just need to take care here. R should be less than s. And here, if tau omega is less than s, and we also need tau omega minimum r is also less than s, we can proceed as follows. So this first is just like 0s times f intersection tau omega greater than s union and here we have 0. Now if this less than s, we have here tau less than s. Let's think for a moment. R is less than t, omega is in f. Let's proceed a bit slower. R is less than t, omega is in f. So tau omega is less than s, which means that this should be of which form? Let's think. Tau omega minimum r is less than s. And tau is less than s. What r are we going to take here?
Can you please go back a little bit to the previous slide?
Maybe I did somewhere a mistake. Now, this is true, right? This is true. If tau is greater than s, this minimum. Oh, here I think I messed up somewhere here, probably. Let's start anew. I need to remove everything, starting from this point. So this is times f, which is r omega, that tau omega less than s is less than s. So we have two cases. R is less than t omega in f, and we need to take into consideration that tau omega minimum r is less than s, and tau omega is greater than s. and tau omega minus r is less than s, tau omega is less than s. Which, in first case, if it's greater than s, is minimum. Let's think. Let me check notes for the previous lecture. I don't remember, actually. I don't remember.
In the second case, if tau is less than s, then the minimum is also less.
Less
So,
is this
so we
automatically,
can
right?
remove this part.
Yeah, it's easier in the second case.
Mhm.
So if you start with the second case, we effectively just have omega less than s automatically. Yeah. And here we have, yeah, I messed up directions here. Here should work, right? So in the first case, we just 0t times f intersection tau omega less than s. This is easy part. Union. What we have here is, let's write it. Omega r less than t omega f tau omega less than s and tau omega greater than s. Aha, now we have what we need. But if you look at the second part, this tau omega is greater than s. So for this to hold, we have r less than s, should have r less than s. So we arrive at something 0t times f intersection tau omega less than s omega r less than s omega f. So this tau omega greater than s. And this can also be decomposed in the proper sense. And because tau is a stepping time, everything is going to be ft measurable. Now, if you look at the proof, so it starts in a very standard ways, and you will try to decompose into two cases, and this is exactly where we will need this specific form of this set, because if you take just here a Borel set, you will arrive at here, and that tau minio still belong to a Borel set, and that's not going to like give you an easy argument. You will need to consider like sections and sections of measurable sets is measurable, but sections of non-measurable sets can also be non-measurable, can be measurable. So let's consider other examples. And f of omega is also progressive, like for any measurable phi. So effectively, everything you can do with Wiener process is again measurable, which is the main conclusion of this example. Maybe we'll also prove it because it didn't went well. So it also, I want to illustrate one idea that works in this case. So I think we will proceed like by taking right continuous approximations. So this is step function that obviously converges even uniformly, almost surely, or just we don't even need uniform convergence, just needs it converge to W T omega for almost all T omega. That's sufficient. So it is sufficient to check that this approximation is progressively measurable. And because it's a sum of such simple summands, it is sufficient to consider one term as a sum. Consider only psi of t equal W AB of t. But now it must be very easy to see why it's measurable. So we again take t less than t fixed. Now we can take any Borel set in Rd, and what we have, we just need to consider R omega in a very similar manner to what we have previously. Omega from here such that omega R psi calculated in this point belongs to this delta effectively. But this is R omega R less than T indicator from AB of R belongs to delta. But this indicator can take only two values. So it's like belongs to delta if this indicator 1 or the same set with the restriction that 0 belongs to delta if this indicator is 0. And I will leave like an exercise to finish this because it's now this part doesn't belong on R, this part doesn't belong on R, is either true or not, and this doesn't belong on omega. So it decomposes in a product of two good sets. But the conclusion that you can take a lot of examples of progressive processes just by taking some functions of Brownian motion. And all in a very similar manner by taking some approximation of this integral, it's very easy to see that this is again progressive. And the last example that is interesting for us is that A is a closed set. We need some assumption in a way for this to work. And then T to the indicator A WT is again progressive. So to see this, recall that we already said that there is a collection of functions that's bounded continuous on Rd such that they converge to the indicator of a closed set. But then this means that phi n w t is progressive, so their limit is also progressive. So you can do a lot of stuff, but just taking functions of Brownian motion or some integrals, because starting from this, you can prove take Lebesgue integrals, etc. Now, let's recall what I was even talking about. Now we can start at last to build Ito integral. So definition, a process psi of t belonging 0 to t, is called simple if I'll use f. There exists a sequence of, more precisely, a partition of the interval from 0 to t, tn, just numbers, and random variables alpha 0, alpha n, such that first, every alpha k is ftk measurable. Secondly, alpha k are bounded. You can just require that they are square integrable. It doesn't really matter. And f of t can be written as such simple sum. Alpha 0 at time 0. And then there's a sum alpha k indicator tau k plus 1 of t. So it's left continuous process. In case of linear process, it doesn't matter. You can take right continuous simple processes, but it matters for other general, for theory of general stochastic integration. Now, it's natural to define stochastic integral for such simple processes than to pass to the limit in a proper sense. So, simple f, the stochastic integral eta. You should write eta with this hat, but I will not do this anymore. Is defined via et of f is the sum from k from 0 to n t, where nt is the maximum number such that tk plus 1 is still less than t, alpha k wtk plus 1 minus wtk plus what is left, the last interval, alpha n t plus 1, oh, sorry, I already wrote it, times wt minus wt and t plus 1. And t from 0 to t. So this is a process. We defined it. It's not an integral, but a continuous. You can check it by hands. This is a continuous process. Why it's continuous? Because it can have jumps only at times tk, but when q approaches tk, this part goes to 0 because wt will converge to those values of tk, and this will just stay as the value of this integral. So obviously notation for this integral that we will eventually adopt and will use is integral from 0 to t f of s dwf. Remark. So if you want to define an ordinary Riemann-Stieltjes case integral, so for, say, continuous Riemann-Stieltjes integral from 0 to t f of s dgs, where g is function with bounded variation, this stuff can be defined as the sum of as the limit of such sums, where tk is just randomly, or more precisely, arbitrary points that live on these intervals. So one can ask whether it's going to be possible for the Ito integral to also consider some sums of this form when phi is a good progressively measurable process. And the answer is actually negative, in the sense that you cannot think about Ito integrals as just L2 analogs of ordinary Riemann-Stieltjes integrals. And the reason is because of the reason why this doesn't work can be illustrated by this proposition. So consider T and K, K and T, K from 0 to T and natural. So natural for me is usually non-negative integer. So 0 is not included in most cases. Then, and this is a fun fact, WT K, WT K plus 1 minus W and K. WT and K is convergent in L2 and to omega, just for fixed T, to 1/2 W squared T minus T. However, if you consider, say, WT and K plus WT and K plus 1 divided by 2, and the same difference here. So if you were working with Riemann-Stieltjes integrals, the result would be the same. There would be like 1/2 of two identical integrals in the limit. However, this is just
I
one.
think we need to take the average of the
No,
T and K, right? So W of T and K
but I
plus T
took
and K plus 1
averages T
divided by
and K
2.
plus 1. What do you
So
mean?
you want to take the midpoint, right?
It doesn't matter. That's a fun fact. I was going to say that you can take here. So you know what Stoyanovich integral is, so you are like meaning this, right?
Mm-hmm.
But the fun fact is this also converges here. So Stoyanovich integral can be defined in two ways, here and here. And in fact, if you want like a general version of this, that for, say, for any alpha belonging from 0 to 1, W T n K plus, say, alpha 1 minus alpha W T n K plus 1, here W T n K plus 1 minus W T n K is still convergent in L2 when n goes to infinity, 1/2 W T minus, and here we will need to put 1/2 plus minus alpha T, I think, for any alpha. So for those who are more familiar with this theory, one can think, but this is also true, but you can write here as this, down nk alpha plus 1 minus alpha Tn k plus 1 instead. And depending on alpha in this expression, you will get the sum that is a different stochastic integral. So for alpha equal to 1, you will have E2 integral. For alpha equal to 0, you will, to 1/2, you will have so-called Fisk-Stratunovich integral, and for alpha equal to 0, you will have so-called backward etostochastic integral. So if you compare this to the case of Riemann-Stieltjes histogram, the choice of this theta k should matter, because even in these two simple cases, you already have different results. So I will prove only the first one, because effectively all the rest is very easy to prove. So effectively what we need is just independence of increments of Brownian motions and some simple properties of their squares. Just to simplify notation. And k from 0 to n minus 1, w and k, delta w and k. And let's try to do this properly. So we want as a result a square of the final value. So we will prepare for that. Plus what is left. And what is left is the original sum. We didn't use it here. And we need to compensate for the first term. Now, this is, because this is like a telescopic sum, it's just 1/2 the squared Brownian process, the terminal time. And here is 1/2 the sum wnk plus 1 minus wnk squared. This is square. Yeah. Which is just 1/2 w squared t minus 1/2 the second variation, two variation, but we already know that this converge in O2. Omega, the first term is just constant, and this is t. So effectively, we already know this, and if you want to prove the second or the third property, just do it more carefully with more terms. Now let's formulate some basic properties of such integrals. So for simple f, f1, f2, we have, this is now a process which is progressive. Secondly, it's linear as a mapping. So for any t belonging to 0 to t, alpha 1 f1 plus alpha 2 f2 is just alpha 1 et f1 plus alpha 2 et f2. The set property is trajectories of this process continuous almost surely. And the force and the last property is going to be about first and second moments. So this is always 0. And the product of integrals is going to be equal to the mathematical expectation of such expressions. In particular, oh, wait. In particular, mathematical expectation ET f squared is just equal to mathematical expectation, so the integral of the square of the s. Now, by the Fubini theorem, because everything is positive, you can write this in this form. And a small remark, why also progressive processes are very good to work, because if f is progressive, and mathematical expectation exists, or even in other cases, then, for instance, this mapping is measurable, and secondly, you can change the order of integration as you are pleased. So this is just the Fubini theorem from calculus. You could recall that the Fubini theorem has two parts. The first part is about ability to change the order of integration. The second part is about measurability of such expressions. So let's look at what we need to prove. So it's very easy to see property this and this, because this is by construction, we defined it to be continuous, and this is also by construction. It's very easy to see that this is going to be a linear combination of those simple summands. So why it's progressive? Again, it's sufficient to consider only the process of a simple form, but we already effectively checked that in previous calculations, so we know that we have progressiveness. So we need to check only that the first and the second moment satisfy those relations that we just defined. And for that, we need to note that if we have alpha is, say, fs measurable, integrable, then mathematical expectation of this expression is just mathematical expectation. We can put additional conditional expectation inside. This is measurable with respect to signal, but sigma algebra can be taken outside. Now, this is independent of the sigma algebra. So it's just mathematical expectation alpha, mathematical expectation WT minus WS. This is zero automatically. But if you recall the definition of simple processes, this is exactly what happens. Those specific values, alpha k, were measurable with respect to ftk when this is independent of ftk. So this holds for every summand in the expression for the stochastic integrals of f. So this proves that this is true. And now to prove that this the relation for second moments is true, consider like fk of t alpha k0 indicator t 0 plus sum. Now consider simple f1 f2 with shared set of support points. Why we can use it in chair? Because obviously we can just add all support points and to write them in the way that they use t k, just t g plus 1 tg of t. So if they have different these moments, we can just rewrite them on the same set of points. Then mathematical expectation et f1 tf2, mathematical expectation sum of j1 j2 from 0 to n minus 1 f like 1 j1 alpha 2 j2, and let's introduce notation g1 psi g2, where psi g is just w2 tj minus w2 psi j is wtj plus 1 minus wtj. Now this is equals the mathematical representations of diagonal terms, which is exactly 1j alpha 2j psi j squared. This mathematical of times the cross terms. j1 not equal j2, alpha 1 j1 alpha 2 j2 psi j1 psi j2. So in the first term we have just mathematical expectation alpha 1j alpha 2j psi 2j f tj, and here we have the same internal sum with respect to a smaller tj1. We just said that since this is ftj measurable, they can be taken out, so we're just left with a square of this expression, and the square of this expression is exactly the difference of those support points that I used to define psi g. So alpha 1g, alpha 2g, tj plus 1 minus tg, because this is a variance of a Gaussian variable. And this is just 2 mathematical expectation j1 less than j2. Again, I will take everything this tft j1 measurable outside. j1, and here we have psi j2 tj1
And we have alpha 1 j1, alpha 2 j2, right?
yeah you're right, like here j1 j2. Thank you. But this is wtj2 plus 1 minus wtj2, and this is independent of ftj1 because this lives on the interval that happens in future with respect to the sigma from algebra. So it's just 0. So the whole term is cross, the whole sum with cross terms disappear, and this is a very standard assumption in the whole theory of L2 integration of some E2 integrals, and we are left just with one sum, and this is by definition of the integral of step function exactly the integral. Yes, because they're step functions, they're like constant on this interval, so it's just this integral and that's all. Now we want to prepare and to extend this to a more general case. So we will need the following proposition. Let f be progressive and such that mathematical expectation from 0 to t f squared of s ds is less than 1. You can see this as technical condition because we want to develop L2 integration, so something should be L2 integrable. However, in general, you can develop it integrals for the case when not the mathematical expectation is finite, but only this internal integral is finite almost surely. But we will not be doing this. But in papers you will sometimes find such integrals, and in textbooks you will also find such integrals, but we don't need them. Then exists a sequence of functions. Every is simple, and phi n converge to phi in L2 omega times 0t to f. So let's proceed in steps. Step 1, sufficient to consider only bounded f. Why? Because we can define fn of t, which is well, fn, indicator that fn doesn't exceed this n. And if we know that every f and capital can be approximated in the sense we want, then we can use the fact, then by definition of the Lebesgue integral, this goes to 0. So we can just take f and t, choose one good approximation for every single fn, and just construct the approximation for our new, for our original. Now, it what follows, I will introduce also notation, the following notation. So mathematical expectation from 0 to t, x squared ds, I will denote as a norm in this sense. And I will use it repeatedly, just to simplify it, to shorten notation effectively. Now, step 2. Now we consider the case. Case when f is almost surely continuous. Surely. So approximations are easy to construct in this case. And this is effectively what we were talking where we were discussing Riemann-Stieltjes integrals. You can take something like this. You need approximation when the value is taken at the left-hand side of the integral you split your original interval into. We already know that this is progressive and well-behaved. And effectively what we need to know, we just need to know that this converges in the sense we want. But how to see this? So like this probability 1. By the Lebesgue dominated convergence theorem, they are bounded and they converge effectively for all t. So they converge with probability 1. But now, mathematical expectation of these integrals square ds also converge to 0 by, again, the Lebesgue dominated convergence theorem. This converges to 0, and these expressions are bounded, so the mathematical expectations of these random variables are converging to 0. Now, step 3. F is bounded and just progressive. This is a bit trickier. Let us define F by setting equal to 0 on negative half x. And I will introduce integrals from 0 to t f of s ds. Or more generally, this t arbitrary. Then a new function is constructed in this way. This is such integral. Now, because f is defined to be 0 outside of the positive half line, this is just can be 0 for very small t and large enough m. The function inside becomes 0 just. So this is effectively, in terms of the previous expressions, this difference. They are continuous because they are difference of continuous functions. And they are progressive also. So there exists, I will denote that m tilde such that first each fm is simple. Secondly, to 0. This is by step 2 because they are continuous and good. Now, by the so-called Lebesgue differentiation theorem, if you don't know, look it up somewhere. With probability 1 for almost all t in 0t, there exists a derivative of the original f capital T. So if you define a Lebesgue integral as an integral of some function, this integral is going to be almost surely differentiable, and this equals to ft with probability 1. But that means that for such omega, for almost all t have, oh, it crashed, as usual. This also means that limit that m goes to infinity exists, because this is a partial case of this derivative effectively, and equals f of t, this probability 1. This implies that phi m of t almost all t phi m of t converge to f of t with probability 1 when m go to infinity. So we just need to consider now with probability 1 integral fs minus phi hat ms squared ds, because these are simple, these are not, is less than integral from 0 to 2 integrals of fs minus fm of s squared ds plus 2 integrals from 0 to t phi m of s minus phi m squared of s squared ds, but this goes to 0. Again, here we use the Lebesgue-dominated convergence theorem. We have convergence almost surely, and we have boundness. And here, because we already said this is, they are constructed in such a way that this happens. So with probability 1 minus this simple process squared and integrated over 0, t goes to 0 when m goes to infinity. Now we again can use the dominated convergence theorems to conclude that we can take mathematical expectation and conclude that this goes to 0, which is exactly what we wanted. We constructed a sequence of simple processes that work. The set of all progressive f such that this iterated integral is finite is denoted by L2. And now this is exactly the set we will define eta integrals for. And to do this, assume phi m are simple such that they converge to 0 according to the previous proposition. Integrals for this simple process are already defined. And we already know by the property of them that this is just a mathematical substitution, integrals of this form. This is exactly limit when m goes to infinity, phi m minus phi n squared this norm. But this goes to 0 because they're convergent to this expression. So again, by that something like triangle inequality. To 0 when n, this is just 0, and the conclusion that the sequence of eta integrals for these simple processes is fundamental in L to omega. So there exists a limit of such expression. And the eta integral of is defined as this limit. L to omega, limit when n goes to infinity, et by n. A very natural question is whether is to ask whether this integral is going to depend on the sequence of approximating simple processes, and obviously this is not going to be true. So this value does not depend on phi n. And why? Because if we have another psi n which are simple and approximate our original f, then the difference between the corresponding integrals e to theta squared is effectively just again the s, which is exactly just the difference. And this is goes to zero because they converge to the same expression in this norm. Another remark is here that we look at this L2 with this norm. To make it a Hilbert space, we need to go slightly more careful in the sense that we consider only on progressive f, but stochastic process is defined up to its version, up to its modification. So effectively, formally, this is the set of all classes of equivalences of progressive processes, but I will not care about such details. So we defined our iter process up to now for fixed t. So now define f from here and any t, a process which is defined by this relation. And this is by definition is denoted by the stochastic integral you see everywhere. Now, because we defined it manually for the smaller t's and t capital, we will need to prove they can be combined in a proper way. So we will need to prove the following proposition. So again, f1, f2, just from L2. And the first one, I, t alpha 1, f1 plus alpha 2, f2 is just alpha 1, et f1 plus alpha 2, et f2. IF is continuous almost surely and progressive. Mathematical expectation always zero, and mathematical just a mathematical expectation of the L2 Cauchy product. In particular, that means the mathematical of the square of a stochastic integral is just f squared now. And this relation is called the iter isometry. Now, because this is true for simple processes, we are taking L2 limits, this automatically holds for their L2 limits, because convergence in L2 involves convergence also first moments and convergence of this stuff. So this is also very easy to see just by the construction, because it's true for simple processes. So effectively, we only need to prove like the second statement. And this is actually the most problematic one. I will need one additional proposition for that. So this proposition is actually redoing some result from the theory of martingale by hands, but since we are not using martingales here and we are not assuming knowledge of martingales, we will just prove it directly. So we have a finite collection of random variables such that they're integrable, and mathematical expectation of psi1, psi-n with respect to the sigma algebra generated by previous is just psi-k. So they effectively just discrete martingale. Then mathematical expectation of maximum over k from 1 to n psi-k squared is less than 4 mathematical expectation of this form. I will prove this again step by step. The first step, let's introduce tau, which is maximum of this collection. So we add 0 here. So this is always at least non-negative. And I'll introduce alpha k of x as a functions, which are indicator that psi1 is less than x, psi k minus 1 is less than x, but psi k is greater or equal than x. So this is one only when we cross the line x exactly at the case step. And claim we are going to prove at this first step is that mathematical expectation eta squared is less than 4 mathematical expectation psi plus n squared, where x plus is maximum 0x, or alternatively 1/2 x plus modulus of x. So we are doing this to make everything positive on the first step. So what follows works. So this sum alpha k of x is exactly the indicator that eta ever gets higher than x. And now we use this trick that the square of a number can be written as the integral of this form. Now, this is integral plus infinity x, indicator that eta is greater than x. So it's exactly two integrals from 0 to plus infinity x, the sum k plus 1 to 1 alpha kx dx. Less than, now, on, if alpha k is 1, that means that all xi's before that were like lower than psi, and psi k is greater or equal to x. So this is less than psi k alpha k of x dx. So we arrived less than 2 mathematical expectation was 0 to infinity. So to make this all work, we need non-negative, all these random variables to be non-negative. That's why we went for this. Psi k dx. But now let us recall that mathematical expectation of alpha kx can be written as a mathematical expectation of a conditional mathematical expectation that alpha k is measurable with respect to sigma algebra generated as the first k size. But this is just mathematical expectation psi n, psi 1, psi k. Now we can take this back because it's measurable, and psi n, this is obviously less than psi n plus, because psi n can theoretically take negative values, which means that mathematical expectation of eta squared is less than 2 mathematical expectation from 0, integral from 0 to infinity, psi plus n, and here stands the sum of n to n, from k from 1 to n, alpha kx dx. But we know that this is just the indicator that eta is greater than x dx. So it just equals 2 mathematical expectation psi plus n, integral from 0 to plus infinity, indicator eta greater than x dx. So this is just eta. We integrate over such x that they are less than eta, so the upper limit is eta. So it's 2 mathematical expectation eta psi plus n, which is less than squared 1/2 by the Cauchy inequality squared 1/2. Now, taking this into left hand side, we obtain following expression. And now just taking squares in left and right hand side, we arrived in our conclusion. And step 2, now we are going to prove the final expression. So mathematical expectation of the sum is less than 4 mathematical expectation of this form, k from 1 to n. Set. This is maximum of 0 minus psi 1. So now we are going to consider negative parts of our original random variables. So we also have such stuff, which is maximum 0 minus psi n. But by step 1, we can say that the mathematical expectation of this stuff is less than 4 mathematical expectation at psi n minus squared. Now combining, can consider the full maximum. Because psi k minus and psi k plus are never take non-trivial values simultaneously. So less than 2 maximums, but 2 maximums can be estimated by step 1 and and the first part of the step. But this is exactly what we need. So this finishes the proof of this lemma, and now we can formulate the result, the corollary of this lemma for simple processes. Be simple, then mathematical expectation of the supremum of the corresponding squares of the corresponding stochastic integral is less than 4 norms. In particular, by the Chebyshev inequality, that means the supremum the probability of this event is less than then 1 over squared mathematical expectation of the supremum, so effectively 4 f squared. And the remark is that typically in textbooks, they formulate a stronger statement where they are able to get rid of this form. So effectively, this is less than 1 over c squared of this norm squared. But I'm not going to prove the more general version. So to do this, let us define the supremum. And let us consider a sequence of partitions of the form 0 t and 0 less than t and n equal t, such that for all n greater than, so starting from some number, all support points of A are in such partitions, which effectively means that so f is constant on intervals from these partitions, on intervals from these partitions. And now we can define eta n by maximum for k from 1 to n, e t n k of f. Obviously, eta n are going to converge to n, and the family for each n, e n n, the e n n f, this family satisfies assumptions of the previous proposition. Because the mathematical expectation of E n and say of f with respect to this E n 1 f E n n minus 1 f can be written as mathematical expectation of another conditional mathematical expectation of a larger sigma algebra, T n n minus 1. And then again, another conditioning. This is larger, it contains more information than this, but this is already integral from 0 to t and n f of s ds, and it's very dws. And because those mathematical expectation from tn n minus 1 tn n f of s dws for simple functions just 0, because this is going to be the difference of values of Brownian motion times some ftn n minus 1 measurable random variable by the definition what a stochastic integral for simple processes is. So effectively, this is just the previous proposition used here. And by using it, you can conclude. So this is all for today. And next time we will finish defining Ito integrals, and we'll prove one of the most crucial results for the whole theory, which is the Ito lemma or the Ito formula. Does someone have any questions, etc.? Well, let me check chat. Nothing is happening. So in that case, I wish everyone good week, and we will see each other in a week.